talks related to modeling, I would say, and mathematical analysis of kinetic equation. When you deal really with fluid kinetic interfaces, one of the major issues at the computational level is how you treat the resulting system of partial differential equation. Let's turn it on. Okay, it's okay. Okay, good. And as you will see, there are several challenges which are related to that. Let me just say that most of what I will present here is done in collaboration with several people here, but the core of this research has been done in a joint work with Giacomo Di Marco from Toulouse. Here is a short outline of what I plan to present. So essentially, I'm going to introduce the problem at the beginning. Of course, the PDE model which we are concerned is given by the kinetic equations. It doesn't really matter a lot which particular kind of kinetic equation. I'm going to use the Boltzmann equation because of its relevance in application, the Boltzmann equation of rarefied gas dynamics, I mean, and because of the challenges that you have. So typically, it's the most difficult collision kernel you have to deal with. But just as a prototype for the development of the numerical methods. I will introduce then exponential techniques for the discretization of this kind of problem. Let me mention that this is not a standard approach, the use of exponential integrators for such stiff problem. So typically, it's well known that exponential methods, they do perform pretty well for highly oscillatory PDEs. But in the literature, there are very few cases where exponential method has been used in order to deal with highly stiff differential equation like the case we are considering here. I will give you some numerical evidence in order to understand better how this method performs, and then I will close with some open problem, further developments, and things we are actually working on right now. Okay, so one of the major computational challenges we have when dealing with the kinetic equation is really the interaction between fluid and kinetic interfaces, so region where you have transition between a macroscopic description of the fluid and the real kinetic description. So these sort of near continuum regimes. Classical example of the difficulties we have is given by rarefied gas dynamics. In rarefied gas dynamics, typically you are stick to Monte Carlo simulation just because of the high computational cost of the collision operator. And in the simulation, what happens is that the quality of the simulation depends on the resolution of the collisional length and time scale. So, and they typically becomes lower as the Knudsen number, so as some reference length scale becomes smaller. More in general, the computation of these fluid kinetic interfaces and the asymptotic limit is really a challenge for numerical methods. So basically, once you have the good model, you're far away from having solved the problem if the final goal is to do a simulation or to make some prediction, because it may be that the challenging to solve the model is larger than the one to build up the model. This is the case, for example, of the Boltzmann equation, which is still, we know the model we should use, but we don't know how to solve it numerical in most numerical application. From numerical point of view, what I will show you that this problem, essentially they involve differential equation with constraints and singularly perturbed differential equation for which we typically should rely on a robust solver for stiff ordinary differential equation. So this is an example from rarefied gas dynamics. It's I would say, probably the most famous application of Monte Carlo simulation. So here, this is the profile. This is the space shuttle. This is a realistic simulation. I mean, the code used here is a commercial code with a lot of parameters in it, all chemical reactions and so on. And you see the profile. This is at Mach 24. The angle of attack is 40 degrees, and we have an altitude of 74 kilometers. The profile you see here along the wing are the Mach number profiles. So basically the velocity. Now, this is just, you can imagine this is just a draft that gives you the picture of the problem, where you have just to take a cross section along this wing, and what you can see typically is that you have an area where a region where the shock is formed. You have a region in the front of the shock where typically the flow is in equilibrium, and you may think to use a fluid solver, but to describe correctly the formation of the shock as well as the profile on the back of the shock, then you typically need to rely on some Boltzmann solver. This is due to several, typically because there are rarefaction effects due to a high speed, which creates, you have turbulence here and several other phenomena. So this is a typical interface. If you want, the shock here somehow represent the interface between our fluid and the kinetic region. I'll show, to understand better this, I'll show here. So we can see at a real-time simulation of this by using Monte Carlo method. Of course, we are doing this now in a simplified environment. So we are just solving the Boltzmann equation, the three-dimensional Boltzmann equation. So there are no chemical reaction, nothing. I'm not, this simulation I'm going to show you is not meant to solve the problem, but it's just meant to show you how the shock is formed. So I don't know, the color maybe is not too visible, but probably is visible enough. Students always like funny color, as Pierre says before. Then you can clearly see here the formation of the shock. The parameters are pretty much the parameter you've seen before. So this is just a Mach 20 flow, and the angle of attack is 40 degrees, and you see the interface that creates where we have the shock. Here on the back you see the rarefaction phenomena. Of course, in order to show you the real-time simulation, we are using very few particles here, okay? So, and the blue area is where the flow is basically in equilibrium. The green area is the area where the shock is formed, the Boltzmann area, and here you have rarefaction phenomena here on the back with also, you see turbulence on the back of the wing. Okay, so to start to describe the problem, I think it's very useful to use a toy model, and more in general, this toy model gives me also the opportunity to stress the link that we have between this kind of problem and another field, which is the field of differential algebraic equation. So if you take a classical problem for people that doing DAE, so differential algebraic equation, is to consider this singularly perturbed problem here. Well, and you can immediately recognize the similarity between this problem and the classical relaxation problem like Jinxin model, okay? So what's missing here is the flow, is the flux. So we don't have a flux, this is just a set of ODEs. But you all know that under this kind of scaling, there's the small parameter epsilon, what typically happens if you take a hyperbolic system with relaxation is that you have a change of the characteristic speed of the flow for small values of epsilon, but this change is induced by the source. It's not at all induced by the flow that you have at let's say, the non-stiff regime. So it's really the source, the challenging thing to treat when you have to deal essentially with small values of your parameter. So typically, let me go on. So what happens is that if you formally send epsilon to 0 here, then this is 0, of course, and you get this differential algebraic equation, so namely a differential equation plus an algebraic condition, which would represent the equilibrium. So if you assume that the unique solution to this problem is V equal E of U, then as epsilon goes to 0, we obtain this reduced set, so this reduced ordinary differential equation. We have just a single ODE. So you also observe one thing, I mean, that if we discretize this guy here, then we are stick to taking a time step related to the epsilon parameter here, so it should be smaller as epsilon becomes smaller, but whereas this is absolutely not required in the limit here, where epsilon is completely vanished. So you have the presence of different scales in the problem that typically create the stiffness of the problem. I mean, by stiff, it's just for people that's not familiar with this terminology. What we basically mean is simply that you have different time scales, okay? One of these time scales typically, or two or whatever, are much smaller compared to the other, and then when you discretize the problem, typically the problem you have to face is that your time stepping typically has constraint that comes from the small time scales. So if you take an explicit method here, then typically what happens is that your time step has to be related to the small parameter epsilon here, and if you take an implicit method, then you have two things you have to be careful. So one is just related to efficiency, so basically you have to play with the numerical inversion of this G of uv, but there's another point which is even more important, is that whenever epsilon goes to 0, your discretization must satisfy the algebraic equation. Namely, when G of u, the solution at the discrete level of the equation G of uv is equal to 0, has to be V equal E of u, okay? And this is not guaranteed if you just take an implicit solver. You need to have specific implicit solver to satisfy that. Well, that's basically, in some sense, what's typically in our community is referred to as asymptotic preservation. This second condition, the fact that you satisfy the algebraic condition. I will be more precise on that later on. This is just to show you the... Okay, now, kinetic equations. Let's consider our general model. So our general model is a kinetic equation of this form. You recognize the similarity with the toy model, so except that I'm using the 1 over epsilon here instead of the epsilon in front of everything, okay? So that this equation, you get it under from the original, let's say, kinetic equation under the classical fluid scaling. If you consider the case of RGD, then this small parameter epsilon here is usually referred to as Knudsen number, which is proportional to the mean free path. And then you have, as usual, the ugly Boltzmann collision operator, which I don't care in the sense that I'm not going to deal with that, but I'll give you an example. This is a very clear example where the inversion of Q of FF would be extremely impractical, if not impossible, in realistic computation. You have a 5-fold integral in every space point. Now, in typical properties of the collision operator are conservation, the Boltzmann operator, which I'm using as a prototype model, satisfies mass, momentum, and energy, and the entropy inequality. From this, basically, what we get is that solution that lives in the kernel of the operator, and you recognize immediately the analogies between this expression written here and the algebraic condition that I wrote down before for the set of dia A, is that f is equal to m only if essentially m as the particular form of a Maxwellian distribution in the case of RGD. In other cases, you can have different kind of equilibrium, of course, like Bose-Einstein, Fermi-Dirac, and so on, accordingly to the problem you're dealing with. So again, it's a prototype. Just think as m as the local equilibrium state of f. So the hydrodynamic equation typically are derived just taking the moments. So we basically multiply the equation for the collision invariant, we integrate with respect to the velocity, and then we obtain the system of conservation laws that correspond to conservation of mass, momentum, and energy, which of course is not closed because it's going to involve higher order moment, because the transport is v times something, so whenever we multiply it by v, we increase essentially the moment that we have to take for f. However, formally, when epsilon goes to 0, exactly as before, the solution of, we get q of ff equals 0, which implies f equal m. F equal m means that f depends just on mass, momentum, and energy, so it's going to depend just on the first moments, and this permits to close the system of conservation laws and to get at the leading order the closed system of the compressible Euler equation. Okay? This is the picture, for example, in this particular case. And you recognize the analogies with what we have presented before for the very simple toy model. Now, some definitions so that we know what we're speaking about. The first, I want to make clear what I mean by asymptotic preserving. So I give a clear definition by asymptotic preserving, which is essentially the same definition which was introduced originally by Shi Jin in his 95 paper on Runge-Kutta methods for stiff hyperbolic system with relaxation. So asymptotic preservation, we define it in this form. We have that if we take a consistent time discretization method for the problem, where delta t is the time step, then we say that the method is asymptotic preserving if, independently of the initial data and of the step size, in the limit, as epsilon goes to 0, it becomes a consistent time discretization method for the corresponding fluid equation. Okay? So basically, what you do, you take your numerical method, you send formally your epsilon to 0. What you should get is a consistent time discretization of the limiting equation. Okay? This has nothing to do, it's just consistency. Has nothing to do with the order of accuracy. So which means that the method can be high accurate for the kinetic equation and can become low accurate for the fluid equation. This is what happens in most cases. So you have reduction of accuracy of almost all numerical methods, but just consistency. You may also have lack of consistency in many cases. So what I will present here, at least in most of my talk, is based on the use of a splitting procedure at the beginning. So if you just, this is a very popular way to solve kinetic equation. I'm going to make some comment about that in the next slide, where you typically split the collision and the transport step. Okay? So it's a classical operator splitting, which means basically in a time step, you first solve this problem, then you take the solution to this problem as an initial data for this one, then you solve this problem in the same time step, and then what you get is your approximated solution to the original problem. I will not make any comment up to now on this, just take it as it is. Now we can immediately state this proposition, which says the following basically, that if you want your time discretization to be AP, so asymptotic preserving, then in the case that you use operator splitting, a sufficient condition is that the time discretization you use at this level, so for the collision step, is such that independently of the initial data and of the time step you are using, in the limit epsilon to 0 as to project your solution f over the local Maxwellian equilibrium. So basically should guarantee that the solution of QFFF equal to 0 is to be f equal to m. Okay? Then of course what you get, you see immediately the consistency, because if here is just a projection, then you get what are usually referred to in the literature as the standard kinetic solver for the Euler equation. Okay? So this is one of the reasons why also the splitting is popular, because you can concentrate all your effort on the collision step and essentially forgetting completely about what happens in the transport step. Comments on splitting method. So first, of course, they are very popular because you can treat in a complete separate way hyperbolic free transport and the stiff collision step. This is essentially the building block of all DSMC code. So it's the reason is that it's very easy to solve the free flow of particle, exact free flow of particle, and then to combine it with a procedure which makes particles somehow collide. I mean, some procedure which is going to change their velocity distribution, essentially. Okay? If we just denote by T and C, essentially the operator of transport and a collision in a time step delta T, then this simple splitting, which usually is referred to as Lee-Trotter splitting or Trotter formula, is it has this representation. Of course, it doesn't really matter that you apply first collision, then transport, first transport, then collision. It's the same. The method is first order accurate. It may be more convenient to do probably first collision because you have first the projection, so you can observe consistency in one time step. Otherwise, you don't have consistency in one time step. That's the reason why it's written in this form. Okay? If you do transport and collision after one time step, okay, if you just analyze the very first, you are not consistent with the Euler equation, so you lose consistency. But I mean, this is not. I mean, there are many curves for that, so it's not a relevant problem. The second order extension is the well-known strong splitting, where you basically symmetrize the operator, and the negative results concerning splitting are the following. First, you have different ways to construct higher order splitting. What you can prove is that if you try to build up splitting method of order higher than 2, then it's impossible to avoid the negative time stepping. So these both in transport as well in collision. It wouldn't be a problem to have negative time stepping in transport, of course, but it's a big problem to have negative time steps in collision. Of course, this is not too bad in practice. It's very bad for Monte Carlo, but it's not too bad for deterministic because practically you can write down 4th order splitting, 6th order, 8th order splitting, where what happens is that what you should do are some very small negative time stepping of the collision part. And this for deterministic method is not a big issue. If the time step is not, the overall solution is going to stabilize as the sum of the different steps. But of course, in principle, it's something that you don't like. Other remark, this is all what I'm going to say about splitting because it's definitely not the main topic of my talk, but I think there are comments which are important in order to understand what are the limitations when you deal with this splitting. They have AP property which is limited to first order. So which means that as you send epsilon to 0, they are consistency, but they are first order consistency. This is just for epsilon equals 0. For small values of epsilon, but not 0, they still perform pretty well. There are results where they show that for stiff differential equation, up to before the limit, they can still achieve the order of accuracy. This is a classical case, is the case of the nonlinear Schrödinger equation, where these are used even for stiff problem, and they still perform pretty well. They keep the order of accuracy. But the problem is different, because when you send epsilon to 0, you have really a singular problem, and then you have really this lack of accuracy in the limit. So you can imagine to get rid of this by taking linear combination of splitting. For example, you take first order splitting with the time step, first order splitting with another time step, both positive, and then you try to combine in the end, in a Runge-Kutta fashion, the solution in such a way that you achieve second order accuracy. Okay? You can do that. The point is, again, there is no way to combine the two steps and achieve order higher than 2 without having negative coefficient. Okay? So you still have to deal with negative coefficient. It's a bit better, of course. It's a bit better because at least you don't have to solve the homogeneous Boltzmann equation backward. But still, for Monte Carlo, this is essentially they are unusable. You can use it with deterministic approaches, but not for Monte Carlo. The advantage is that you can build up these in such a way that you keep the order of accuracy. So you are second order, and you are second order also for the limiting flow. Okay, that's all I wanted to say about splitting method. It's not the main topic of my talk, but these things should be made precise in order to understand what's going on later. Now let's come to the core of what I wanted to say. So the problem that we have now to deal with is the following. We have to deal with this stiff differential equation. And what we want to avoid is the inversion of this operator here, Q of ff, because if we take a full implicit method, then we need to solve it by several iterations. Every iteration involves the solution of the collision operator, which is exactly the highest computational cost in the simulation. Okay, so let me start from this let me start to rewrite the collision step in the following form. Let me just take a constant value mu in such a way that Q of ff plus mu f is some operator which is non-negative. Okay, at a numerical level, this you can always do that. It's not even for the derivation of the scheme. This is not even mandatory. In fact, we are gonna get rid in practical of this restriction, but it's very convenient in order to give to derive the scheme and to present it, because you're going to understand better basically what's going on. That's at least my feeling. So by construction, if we take this operator, which is basically realize this mu should bound essentially the largest spectrum of the loss part of the collision operator, then you get this representation. So you get this function, this P of ff over mu, which has the same moments of your function. So this is a distribution function. It's a non-negative. So in principle, we can take a micro-macro decomposition of it. So we can just decompose it like Maxwellian plus some reminder. Micro-macro decomposition has been widely used in the literature at different levels. It is just a very short list of references and people that worked on that. Okay. In most cases, you don't decompose the collision operator, you just decompose the distribution function f. You get something very similar, actually. You don't, there are, in this case, I think it's more convenient to use this decomposition, but you can achieve similar result also if you decompose the distribution function f. So if we insert this into the collision step, this leads to this formulation, which has been recently presented by Francis Filbé and Shijin as a penalization method for the operator based essentially on adding and subtracting a linearization of the operation of the interacting operator close to the fluid limit. There's something interesting in this in their viewpoint if you think at it, because in most numerical methods what you typically do is that you penalize the operator with a linear operator. That's a very classical procedure to avoid the stiffness, but you always do this for short times. Okay, you do the linearization starting from your actual solution. In this case, you do the linearization, which is just works asymptotically. So you do it on the equilibrium state. Okay, that's what happens. There are also other ways to derive essentially this formulation, but that's I think the way I've decided to present. Of course, I mean this problem 1 is absolutely equivalent to our original homogeneous equation. We are just adding and subtracting term. There's no change. Okay, which means basically that there's no way we have removed any sort of stiffness in the operator, because the operator is stiff as a wall. Okay, so it may be we would be tempted to say, well, okay, now eventually this contains the stiff part, this does not, this is less stiff or whatever, but this is not the case. They have absolutely the same stiffness. So the real point is that what we can think is the following. We may hope that this term here, as a penalization factor, since it's linear, is going to stabilize the instability which are originated from here. Okay, this is basically the idea. Okay, so far so good. Then I'm going to show you some related things. So keep in mind this formulation we have derived in this form. Now, let's just rewrite. This is formulation 2, which is equivalent to the one we have seen before, just by taking the integrating factor e to the mu t over epsilon. Let's rewrite this in this form, and then just Taylor expand along this time, the rescaled time, and use the bilinearity of P of ff. Then you can prove the following, that the solution to your problem can be represented exactly in this form, which is a Taylor series expansion along this term here, which has much in common with the wild sum for the Boltzmann equation for Maxwell molecules. Okay, except that now you see you have the presence of Maxwellian terms here. Now, what's very interesting is the following. Now just take a simple truncation to this term here. Just truncate this series, we are going to have a numerical method for the previous problem, okay? Let me just say, I mean, we have this recurrence formula for the terms here, which are simply obtained by the fact that in a Taylor expansion you would have derivatives, right? But you have derivative of a bilinear operator, okay? Then you evaluate that subsequently in a recursive way. You originate trees, essentially, of subsequent evaluation of the collision operator. That's the way this builds up. Now, let's just take a simple truncation here. If we just take a simple truncation, what's very interesting is that you get exactly the method which were introduced a long time ago by myself with Giuseppe Toscani and Esther Gabetta in '97. Actually, it was my PhD, part of my PhD thesis, so really a long time ago, I'm sorry to say. When we did, however, that derivation, we haven't been able to derive those directly from the equation. They were derived by applying some penalization method and then by making physical consideration about the behavior of the FKs. But what is really interesting here, that you get exactly, so they correspond exactly to a truncation of a Taylor expansion to the modified problem when we add and subtract, okay? If you think at this now, it's somehow obvious. It's somehow obvious because basically you have two ways to introduce the penalization. One way is to add and subtract the BGK. Another way would be take the solution and add and subtract the exact solution to the BGK. So what we are doing here with the time relaxed method, what we are basically doing is adding and subtracting the exact solution to the BGK, which is of course equivalent to add and subtract the BGK term in the original equation. So why these are interesting? Well, they are interesting because you can immediately see here that the weights are all well posed independently of the small values of epsilon. These are all bounded in 0, 1. The FKs, they satisfy this nice property of being probability density function. This property is induced by the choice of mu we did at the beginning by the structure of the operator P. So basically what you observe is that this scheme are a nice convex combination of non-negative densities. In this way you satisfy basically a lot of good properties. In particular, they are asymptotic preserving, so which means that if you send epsilon to 0, all these terms are going to vanish and this becomes equal to 1, so you have the Maxwellian. And they are exact, of course, for BGK operator, because it's exactly what we did from the beginning. So they're exactly, every time that Q degenerates into the linear BGK, the scheme collapses automatically toward the exact solution of the BGK. Okay, so this was done a long time ago, okay, but it's very nice, I think, the new derivation we have of the scheme, because it puts in straight direct connection with the equation. That's thanks to the reformulation introduced by Francis and Shiji. So why this scheme? I mean, the scheme has several nice properties. So from a theoretical way, they are really nice for the homogeneous equation. You can prove that they are contractive once you have a contractive metric, like the one introduced in the paper by Toscani and Cedric. For example, the Fourier metric or whatever metric, such that you have an estimate like that. You have this kind of estimates typically for Maxwell molecules. This is the case where you get this kind of estimate. If you define an entropy functional, another very interesting property of this scheme is that they satisfy unconditional entropic stability, so which means they are entropic. Let me also point out that entropic stability is really a challenging property for a numerical method. In fact, the entropic stability is absolutely equivalent to the notion of strong stability, which has been introduced, for example, by Eitan and co-workers for partial differential equation. So what is known is that except for implicit Euler, all other Runge-Kutta method, they cannot satisfy this property, so they cannot satisfy entropic stability unless you take some time-step restriction. So even if they are full implicit, they are not entropic. You have, again, to take some time-step restriction. Is this important for application? I would say no, in general. But it's quite interesting from a theoretical viewpoint, or if you want to study, for example, just the numerical solution of the homogeneous equation to check for conjectures or whatever it is. So when you need very, very accurate solver, this can be an important remark. So all these schemes are entropic stability. So in the language of more general language, they satisfy the strong stability preserving property. There are limitations. Well, of course, they are operator dependent. They strongly use the bilinearity of the operator in the derivation. The way they are written is not really a standard Runge-Kutta notation, and you may say, well, this is not so relevant, but it's really relevant for a lot of people. I had people that refuses essentially to implement it just because, well, they didn't look like a standard numerical method. They look like more some iterative solver at some level. And this may also make difficult to, for example, to code it and to just plug it into an existing code. And of course, they are based on operator splitting. This is not necessarily a drawback. It's a drawback in terms of high order accuracy, as we've seen, but it's important if you want also to have something that works with DSMC. Now, let's move to the next point is how we can generalize this approach now and to consider a more general application where we are not related to any bilinearity of the operator, that we can essentially apply to in a more, let's say, standard framework from the viewpoint of numerical method. So now the starting point is we take this system of ordinary differential equation here as a prototype. You see this g of y is what remains, if you want, between the difference between your collision operator and the BGK. And this is the linear relaxation operator. Of course, g of y is equal 0 only if y equal a, so both operators, they share the same kernel. The idea is that to use this linearized operator in order to penalize this operator here for large times in such a way that you achieve stability. This has a lot in common with the classical application of exponential method to equation where you have a linear operator and a nonlinear operator here, and you try to integrate exactly the linear flow in order to derive the numerical method. So this is the general formulation. I don't pretend you're familiar with this formulation, but it's just to write you what you get. So typically, when you deal with Runge-Kutta, what you write down is you have this series of coefficients and the series of weights, and then you match with this coefficient and the weight the Taylor expansion of the solution up to some order. Then you get some order condition, and then you try to satisfy algebraically this condition. So far so good. There are different ways, of course, to build up an exponential Runge-Kutta. I'll show you. It's very easy to derive one family of this method, which is so-called the integrating factor family. The other family are the exponential time differencing method, which I will not consider here. So if you want to derive what is called integrating factor method, what you have just to do, you just reformulate your problem by using the integrating factor here, okay? And use the fact that the derivative of E with respect to time is 0, like in the homogeneous problem with the Maxwellian. Then you just apply any standard explicit Runge-Kutta to this, and then you revert to the old variable. These are the coefficients you get in this case. For example, if you apply it to the Boltzmann equation, that's the first order method you get. I'm going to show just you low order method when I produce down, even if you can build up higher order method as well. This is, for example, the first order scheme you get in this form. You see, it has something in common with the above discretization originated by the time relaxed, and in the sense that it's still a convex combination of 1, 2, and 3 guys, which are probability densities. So again, you can show that you satisfy non-negativity. Asymptotic preservation is also contractive in the case of a bilinear operator with some contractive property, and entropic stability is satisfied. The major difference you see is that the way, it has this coefficient here, which is going to replace the term that you had before, and this term is going to relax at a slower rate, so somehow they're going to relax slower toward the Maxwellian. But we are still just, they are first order method, and we can't really hope that they can work for all regimes by keeping a high order of accuracy. So we can state 2 theorems. Every talk should have a theorem. Here I have even 2. So the first theorem concerns contractivity. So what are the conditions we should impose in such a way that contractivity is satisfied? Well, the conditions you get are basically that for a given, of course, contractivity depends on the metric you use and the operator. So I'm thinking to a metric that satisfies the condition we have seen before, is that we should have a new stage explicit Runge-Kutta method of order nu with non-negative coefficient and weight which satisfy this. Okay? Well, again, what in practice this means the following: that you can use any Runge-Kutta method up to the order 4 explicit Runge-Kutta method, because you know that the order 4 is the barrier up to which you have non-negative coefficient and weights, and the number of stages matches the order of the method. To be honest, the classical fourth order Runge-Kutta is the unique scheme that satisfies at the fourth order this property. But this is just for contractivity. What about if you want convexity? So if you want entropic inequalities and things like that, and if you want to have a convex combination of probability density, so to such a way that you can blend the method into a Monte Carlo formulation, then you perform some analysis and you get this kind of more restrictive condition, and this excludes several methods actually, even up to second order. It's going to exclude, I would say, the majority of second order methods. Okay, but still, rather standard second order methods are included in the derivation. The classical, among the two classical Runge-Kutta methods, the typical which are used, the Oin method is excluded, whereas the Runge method is kept by that. And it also excludes the fourth order method with 4 stages. So if you want to go to fourth order, you have to play more. But I mean, I think it's nice to understand the way it works. It was not really my goal then to construct very high order method or whatever, to see up to which you can move and to have a general theory for that. Okay, so just to show you some very simple example, let's start with a toy model, Kath equation, exact solution. This is what we do is that we compute the L1 error in one single time step, which means basically all the solution you see here, it's a continuous profile, is computed just in one time step. Every time I'm jumping from the initial data, I jump here, I jump here, I jump here, I jump here. It's not a series of subsequent steps, okay? So to compute the solution at t equal 18, I'm using a time step t equal 18, okay? Just from the initial data, it's just one time step. You really see the AP property in this way. For example, what you have here, this profile here, is the profile you get with the original time relaxed scheme. These are the first order, this is L1 error. This is the profile you get with the first order integrating factor, which behaves a little bit better. And the dashed line you see here is implicit Euler, which you see is less accurate actually. Of course, if you go to second order, this is the second order method, then you observe again, you see this is the error curve for the second order method, which gives a better profile as you expect. This is an example of a method which is not AP, just to show you what happens. So basically, it's able to follow the solution up to a certain level, and then even if it's stable, then the solution is going to just diverge. The method is stable, but it's not AP. It's going to project towards something which is not the local equilibrium. This is the full Boltzmann equation. This is the computation of the fourth order moment, and these are the L2 error you get by considering different time steps. So basically, you can imagine that the blue line is the borderline of stability of explicit Euler. The green line, we take the time step is 2 times the time step of explicit Euler. The black line, the time step is 4 times the one of explicit Euler. So this is somehow, if before it was really a test for just to see the asymptotic preserving property, this is a different kind of test. We are performing a classical simulation of the 3D relaxation of the Boltzmann equation to see how accurate they are in time. If you draw a line here, you can show that there is first order convergence of the method. This is the second order method. This is the second order method, and you see again, when you reduce your time step, the second order convergence. And this is the third order method. And you see, I mean, here we are the computation becomes challenging because the error is 10 to the minus 8 basically, okay? So it means that you need to have a very accurate evaluation also of the collision operator, okay? What we are using here, we are just overkilling the problem for the collision operator, just taking it, we're using Monte Carlo actually, but just with a huge amount of particles. We didn't care. I mean, we just want to be exact for the collision operator. It's not our issue here. It's just time discretization part. Okay. So, okay, now this is an interesting problem. We consider a non-homogeneous problem, so now we have splitting in it, and I'm considering the classical SOT test, but I don't want to measure the error on the classical conserved variables, but on the variable that must satisfy somehow the algebraic relation. Okay? If you want to see the real projection towards equilibrium, what you have to compute is the error for the non-conserved quantities, like a heat flux. The heat flux goes to 0, of course, in the limit as the Knudsen number goes to 0, okay? And that's basically the algebraic condition you get as epsilon goes to 0. So we measure the heat flux for a small variation of epsilon. This is pretty challenging for a numerical method because then you really observe if the method essentially solves correctly the equilibrium projection or not. This is essentially the first order method. This is, let's say, a moderately stiff regime. We are still in the stability region of explicit Euler. Let me mention here that it's not just, I mean, you have also the transport. So the time step comes from the transport, okay? This basically means, when I'm saying this, it means that I'm using here exactly you can use the time step in the transport, the time step on the explicit Euler in the collision to be the same, okay? And this is the first order method, and this is the second. So you see how time becomes important. I mean, time discretization is usually, if you plot shocks or things like that, you don't see a lot of difference. It's much more, the real role is played by space discretization. But if you plot non-conserved quantities, you can really observe the relevance of time discretization. So this is, we move into here we are much closer to a Navier-Stokes regime, and this is the first order method. You still, I mean, you observe some fluctuation. Again, all reference has been computed by DSMC. So even if we were using a lot of particles, there were still some small fluctuations in the solution. But from a qualitative viewpoint, the profile is not gonna change at all. And this is the second order method. You see again how you catch this. The much better the structures of the solution for the second order method. And this is, for example, that's really, I mean, we are approaching very small values of epsilon. Here our time step is 10 times larger than an Euler time stepping. The epsilon is 10 to the minus 4. We are basically approaching the 2 deltas where the shock is, okay? And so it's very hard to, of course, to compute, but this is the first order method. What is important is that at this level, you know that your splitting is going to lose accuracy as epsilon goes to 0. We knew it from the beginning, okay? But still, you see how it's important to switch from first to second order. You have a marked improvement in the resolution, which means basically that if you want really to have something which is consistent with Navier-Stokes or whatever, high order is an important property in time for the numerical method you're using. So I'm going to just close now with some further developments. So what about if we don't take time splitting from the beginning? So what about if we just try to develop something which is not based on time splitting, which means basically that our main interest now is for deterministic application, no more for Monte Carlo application. Well, the situation is a bit more difficult, of course, because what's the main difference? You can always have this general formulation. You simply put your transport into the G. Okay, you plug into the transport is non-stiff. It shouldn't create a big problem. But what the major difficulty here is that namely the equilibrium, depends on time. So the integrating factor formulation we have seen before is no more valid because it's no more true that derivative with respect to time of E is equal to 0. So we cannot follow the previous approach and just apply the schemes. What you can do, however, you can write the solution in exponential form, and you can write it in this way. And then what you have to play, the game you have to play is the approximation of these two integrals here. This one here and this one here. This is much closer to what is called the exponential time differences in the community of people that's playing with exponential method. So now you have to be careful. What I'm just showing to you is how you can do, for example, to get a first order scheme. Up to now, I've succeeded to get first and second order method, no more than second order. So you just take an approximation of this. This is pretty easy to approximate because basically you want just that the term e to the minus lambda t is going to squeeze everything to 0 because this doesn't play any role in the asymptotic limit, whereas this is more difficult to approximate. You have to be careful because you have to approximate, they both are singular. You have to approximate these in such a way that you get the asymptotic preservation and that you keep also the order of accuracy. Okay? So this is, for example, the first order method you get. The major difference is that you see now you have the presence of the Maxwellian at time n and at time n plus 1. So how you solve the Maxwellian at time n plus 1, it means that you need to solve the Euler equation. So on the top of this, you have the solution of the Euler equation. Okay? It's not the Euler equation, the moment equation, sorry. So it's the moment equation where you simply plug your f in order to get rho, u, and t at the next time step. Of course, the solution, the solver used for that moment equation system has to have the same order of accuracy of the solution you compute here with the numerical method. Okay? In this way, you get a scheme which never requires the solution to invert the collision operator, and it's AP. Another approach is the IMAX method. IMAX method, there have been, which means basically that you have to use an implicit, the most standard idea if you want. You have just this problem here, and you would say just, okay, let's take this explicit, this implicit, and hope for the best. Okay? Why not? Well, it turns out that this is not such an easy game to play. Implicit, explicit Runge-Kutta method has been studied by several authors. Together with Giovanni Russo, we essentially develop some conditions for this method to be AP for a certain class of problem, but it turns out that the usual condition we have for the AP property is not enough in this case. And this is not surprising because typically you use explicit implicit to integrate a flux which is non-stiff in an explicit way and the source which is stiff in an implicit way. Whereas now here you're playing just a game where you hope that the linear part is going to stabilize the explicit part which is also stiff as the remaining term. Okay? So that's the reason why they do not preserve the AP property. What it can be proved is that if you add one additional implicit stage, then you can achieve AP property, which means that if you want to have a first order, you need to have 2 implicit stages, second order, 3 implicit stages, and so on. This is not a big issue. You shouldn't be worried about that because these implicit stages concern just the solution of the BGK, not the solution of the Boltzmann operator. This is, for example, the first order method, which is AP. You see, that's exactly the scheme that was used by, for example, by Shijin and Francis, which is you would say the most straightforward first order discretization of your problem, which on the top of it, it has just an homogeneous BGK relaxation. This is just going to project the solution towards equilibrium. Okay? Of course, it's not derived on the basis of physical consideration. It's just derived in the framework of Runge-Kutta method by applying the order condition. That's what you get in practice. Okay? So you can also understand that practically, since this is first order in itself, you can also think that for practical application, you can even just apply this not necessarily at each time step. You can just apply it just for the very first time step and then rely to a scheme, to the standard scheme, which doesn't include this one. Okay? It's a little bit more tricky when you go to second order, but you will see the core idea is always that you have steps like this one at the beginning. Okay, so I think I can go to my concluding remarks. I hope that I have convinced you that exponential method, they really represent a powerful tool for the approximation of kinetic equation. It's as I was mentioning at the beginning, is a non-standard application of exponential methods. So they're never applied to highly stiff problem as we have here. The nice thing is that it's easier with them to satisfy convexity property, which gives you non-negativity and monotonicity of the solution. So they are very well suited, especially if you want to have things where you use Monte Carlo evaluation of your collision operator, which is not so easy to do if you use other kind of discretization. You can also think about non-splitting strategies. They are a little bit more tricky, especially with exponential method, but otherwise you can use IMAX method and you have to add additional condition as we have seen. These methods are interesting because you can blend it essentially in existing codes like domain decomposition or hybrid method. Of course, if you have domain decomposition, the point is you have to stick on the kinetic side on some interface region, and so you need to be efficient in terms of solving, okay? So the more efficient you are in the numerical solution of your kinetic equation, close to fluid regime, the better you can basically blend the kinetic and the fluid solver, or into hybrid techniques. Here is, again, list of people, incomplete list of people that work on this subject. There are several extensions and applications of these ideas. So of course, quantum kinetic equation is a field where you can think to apply this. You cannot apply the time relaxed, but you can apply the integrating factor method because the operator is fourth order. So you can apply the new schemes which are being derived here. Landau-Fokker-Planck equation, this of course is slightly different because you cannot linearize them with the BGK, but you can linearize them, for example, with a linear Fokker-Planck equation, just as a stabilizer. What is important is that you keep the asymptotic state. Let me do a final remark about it. Since you're playing the game of basically forcing your method as a stabilizer to follow the linear flow for large times, you have to be careful. So high order may be really important, because even if the method is stable, you cannot expect that the method works pretty well, because when you go in the very stiff regime, what you're basically doing, you're saying, okay, let's use the linear model. If you're thinking it from a physical viewpoint, let's use the linear model to stabilize everything. If you are high order, this linear model is gonna play a role just in higher and higher and higher order term. So you have a much better profile. So this is just to say that even if you blend it, for example, into a first order method, it may make definitely sense to still use a high order method to solve the corresponding collision step, because you want to avoid this potential effect of over relaxation, or basically of, let's say, BGK approximation of your solution. Granular gases, this may be challenging because the steady state is non regular, but you may rely on some self-similar approximation and try to build more or less the same game. Nonlinear diffusion is also an interesting application. You use the self-similar formulation of nonlinear diffusion, okay, and then you have, and then you can again play this game. This is there are, however, some theoretical aspects here, because, for example, if the steady state is non-regular, like in the Barenblatt solution, then your linear problem typical loses the regularity of the solution immediately, and so you're going to observe artifacts on the solution. So it's still an open problem which kind of good linear problem you need to use here. This is the question I posed to Jose here. Related topic is diffusion limit. Of course, diffusion limit is slightly different, but it's interesting that you can use some of these techniques. In recent work with Sebastiano Boscarini and Giovanni Russo, we developed a general approach to diffusion limit, where you also get full implicit method in the limit, so you treat the limit in nonlinear diffusion in an implicit way, which somehow relies on some of the ideas that I've presented here. Okay, thanks a lot for your attention.